So now we need to discuss what are the problems we may find when we look at a function and why it may fail to be continuous at a point. So there's a classification, if you will, of discontinuities. The first kind is that of a removable discontinuity. What does this mean? So if the limit of f of x as x approaches c exists, but the limit of f of x as x approaches c is not equal to the value of the function, we say that f has a removable removable discontinuity at x equals c. So what is the idea? Why do we call it removable discontinuity? Because in order to have a limit when we approach a number c, from the left and from the right, the function must be approaching the same value, so some value over here. So this has to be the limit L. So this is f of x. In this graph, the limit as x approaches c of f of x is equal to this limit value L. And however, f of c may be something different from this value, so this would be f of c. Okay, so f of c is not equal, in this case, is not equal to this limit, which does exist. Okay, but the function looks more or less like it wants to be continuous. So if we were able to redefine the value of f at the point c and move this point downwards and make it fit the graph, I mean, we could fill in the hole there and the function will be continuous. This is an unlike situation where we have, we'll see next, where there's a jump. There's no way to assign a different value of f at the point to make the function continue to repair the graph. Everything looks continuous here except that the value of the function does not agree with the limit, but the limit exists. So if you approach something from the c from the left and from the right, f seems to have a trend and it seems to be converging to a point to a value L. So if we just assign that value L to f at the point, then we'll have a continuous function. So in that sense, it's removable because we can remove this discontinuity by simply redefining the value of f. That's not the case for other discontinuities. One important thing here is that whenever we write something like this, like the limit exists, but it's not equal to f of c, that also includes another piece of information we may forget. The thing is that f may not be defined at the point. And so if f is not defined at the point, but the limit exists, then it is certainly not equal to the value of f at c, because f of c is not even a number. You have not assigned a number to f at the point, and therefore the limit cannot equal something that does not exist. Okay, so that's also a removable singularity. So even if there was no value assigned to f at the point, this will still be a removable removable discontinuity. So that's a first kind of discontinuity that we may find, and it's the least serious because we can repair continuity by hand by reassigning the value of f at the point. But then there's a second more serious kind of discontinuity. Jump discontinuity. That's the second kind. And this happens. So this occurs if the limits from the right and from the left of f of x exist, both of them. So we do have right and left and limits. But, and here's a big but these limits do not agree with each other. So in particular, the limit doesn't exist. So there are, we will look at some examples of graphs where this happens. This is the case, and so let's suppose we have a graph like this. So this is number C. And here in this, well, in this, for this particular function, we see that the left-hand limit is actually equal to f of c. So only will only be left continuous at x equals c. And the limit from the right also exists, but there's some other value up here. So the function is has has one-sided limit, and one of them actually coincides with the value of the function, but the left-hand limit and the right-hand limit do not agree with each other, and therefore the function is not. I mean, the graph of the function has a break, and therefore function is not continuous. It can also happen. Another example, visual example, is the following. So you have a similar thing. Only now the value of the function does not agree with either right or left hand limit. So this is a situation where function is neither left nor right continuous at x equals c. And the idea here for this kind of jump discontinuity is that we that's why it's not removable, so we cannot fix it to make the function continuous. Unlike the case of removal discontinuity, where if we were allowed to redefine the function at the point, we would obtain a continuous function here, no matter what you choose for the value of f of c. Function will not be continuous because the limit doesn't exist. It's a right and left hand limit, even though they actually exist, they are different to each other, different from each other. And this actually allows us to, so here I've talked about um, left continuity and right continuity. Right, so this is something that I've introduced very loosely, but let's define then what we mean by that. It's a good idea to introduce this notion of one-sided continuity, because a function may not be continuous, but may be one-sided continuous, and that may be good to know. Um, the function may behave nicely on an interval, but not on the whole real line. So you will still repair continuity if you restrict the domain of f. So left continuous is set. The function is to be set to be left continuous at a point x equals c if the limit of f of x as x approaches c minus is equal to f of c, and it's now right continuous well it's right continuous now at x equals c if what you imagine holds. So the limit of f of x as x approaches c from the right is equal to f of c. So that's one-sided continuity for you. So you just check the definition of continuity by replacing the limit by this one-sided limit. And this leads us to a number of examples you will see often in exams or in problems, homework assignments, and such. These are what I call piecewise defined functions. Okay, so sometimes you will be given functions that are not defined globally, so there's not just one formula that tells you how to, a rule that tells you what to assign to each number, but there will be like partial rules that will only apply to subintervals of the real line. And you'll need to analyze those functions independently and see what happens at the transition points where you change from one formula to the other. So let's consider this function, say f of x is equal to f of x, capital F of x, which is equal to f of x, so little f of x for values of x smaller than a certain number k, and g of x for values of x greater than or equal to k. And you can actually use multiple functions, and you can divide your the real line into as many subintervals as you want, and define functions in a piecewise manner that way. For example, let's try to study the continuity of the following function f. Capital F here is defined as x squared for x less than 2, 5, so just a constant for values of x between 2 and 4, and x plus 1 for values of x greater than 4. So f of x equals x on the entire real line, and g of x equals a constant 5, and finally function h of x equals to x squared, as we saw, are continuous. All continuous functions. This is the last example of x squared we just saw not long ago. But the function is neither f of x, g of x, nor h of x. Right? So we need to check what check what happens at the transition points, because the function is not equal to f, it's not equal to g, not equal to h, only in subintervals. So when you move from one interval to the next, you need to check that that transition happened in a continuous way. But we have to check the transition points at x equals 2, so we'll see the one-sided limit exists, but not equal. The limit of f of x, so x approaches 2 from the left. If you're at the left of 2, it means that you're in this interval, so x less than 2, so that means that f of x is equal to x squared. So you'll be computing the limit of x squared as x approaches 2 from the left, and we already know that that's equal to 4. However, what happens when we compute the limit of f of x for values slightly greater than 2? So when we're computing the limit from the right, if we're computing the limit from the right, that means that we're here in this interval, not here. No, because at the, remember, we're approaching 2. So we're very close to 2, it's just that we're a little bit bigger than 2. Right, so just so we're between 2 and 4 for sure. And on that interval, f of x, capital F of x, is equal to the function 5, the constant function 5, g of x. And when we take the limit from the right of the constant 5, it just gives us that constant 5. So f has a jump this continuity at x equals 2. Now if we do the same thing at x equals 4, we see that the limit of f of x, so x approaches 4 minus, is the same as the limit of 5 excuse me, 4 minus, so we're approaching 4 minus. Why? Because f of x, when you're close to 4, but slightly to the left of 4, it means you're you're inside this interval. So x is slightly smaller than 4, but it's very close to 4, so it's certainly bigger than 2. So inside that interval, f takes on the value 5. And so that's how we compute the limit. We place f by 5, and we compute the limit of 5 as x approaches 4 minus, but 5 doesn't change. So the limit here is 5. Also, the limit of f of x as x approaches 4 from the right is the limit of what function now? Again, we're approaching 4 from the right. So we're looking at values of x that are greater than 4, but close to 4. That means that we're inside this interval. And here, f of x is defined as x plus 1. So we take the limit of x plus 1, and we can use the sum law, and we get that this is the same as the limit of x as x approaches 4 plus the limit of 1 as x approaches 4 plus, which gives us 4 plus 1, which is equal to 5. Okay, so both left and right hand limits exist and are equal to each other, right? So what remains to be seen to check whether or not f is continuous at the point 4? Well, what is f of 4? We need to look at the definition of f again. So this here tells us what is the value of f for values smaller than 2, so certainly not what happens at x equals 4. This only deals with the value of f for values greater than 4. This, however, includes the value of f at the point 4, because here the requirement is that x is between 2 and 4, but including both 2 and 4. And inside here, the value of f is 5, right? So including both endpoints, 2 and 4. So that means that f of 4 is equal to 5. So now we see that then we see that the limit of f of x, so capital f of x as x approaches 4, when I'm just talking about the one-sided limits, because we already checked that both right and left limits are equal to 5, so the whole limit exists, and it's equal to 5, which is equal to capital F at 4, which is what we just checked. And so therefore f is continuous at x equal 4. Right, so to finish this is a little bit longer than usual video. Let's look at the graph of the function capital F to visually over it. talking about the 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. We have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So between minus infinity and 2, capital F is equal to x squared, but it's not equal to x squared at 2, so you have a hole there. And in fact, between 2, including 2 and 4, between 2 and 4, the function is equal to 5, so you have a horizontal line there. And from then on, it's equal to x plus 1, which actually starts from 4. And thus the function looks like that. And you can see here, I mean, visually that the function was not continuous at 2, but it is at 4. Okay, so that concludes this part of this video, and we'll continue in the next one. This is one. It's getting a little longer than what I expected.